Hey everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials and Manufacturing Innovation. In today's paper, we're going to talk about attempts to try and model melt pool size in additive manufacturing using surrogate modeling. This work comes to us from two authors, Corbin, Grohol and Young C. Shin at Purdue University. Now, this is a well-known problem. Trying to model the melt pool size is important. But there is complex thermal cycling and a variety of defects that all come as a result of this, right? The pool size impacts the cooling rate, which impacts the microstructure, which impacts defects. So it's important. And there's been a lot of attempts to try and model it over the years. For example, the authors point out that there have been mesoscale models, right? Ranging from conduction models, which are sort of like on the low computational end, all the way to the high fidelity, high computation end of computational fluid dynamics models, and everywhere in between. So the trade-off here is that these high fidelity models, they offer more accurate predictions, but they come at extreme cost. I just put it in perspective here. It can take several days of computational time to simulate a laser scan distance of only a few millimeters. So you can't really do the whole part, let alone anything beyond a few millimeters. The authors spend a lot of time describing the different modeling efforts that have been deployed before finally mentioning that ultimately this comes down to a dilemma where you want the accuracy of the high fidelity model, but you want the computational reduction of these lower fidelity models. And is it possible to have your cake and eat it too, right? They point out that heat conduction models are computationally efficient and they can be applied to the larger domain multi-track cases, but they typically have low accuracy. So in this approach, this paper, they're going to try and develop a surrogate model that takes advantage of both these things so they can actually do modeling of multi-track scan patterns while achieving the high fidelity and the low computational cost of both of those different modeling approaches. So how are they going to get the best of both worlds? Well, the way that they're going to do it is they're going to actually generate training data for a surrogate model by running both the high fidelity model and the conduction model on this 3-track scan pattern of a molten pool where the width and the depth are extracted at a high frequency. And then they're going to train the model using just the CM predictions as inputs and try and predict the HFM as the outputs, right? Take in the low fidelity data as your input and be able to predict the high fidelity. Pretty interesting, right? By trying to output this high fidelity prediction, they could potentially, if they learn how to make that mapping, that correction function, they could then be able to predict the entire area. So their workflow looks something like this. Generate data where you're simulating over the same 3-track region with both models at these 2 different temperatures. Train a surrogate model using that data. Simulate the conduction model over that entire pattern. And then input these CM predictions from step 3 to the trained surrogate model from step 2 to predict the high fidelity pattern for the entire pattern. So this figure right here shows you what the different data actually looks like from both HFM and CM. So you can see the trade-off in fidelity and resolution when they're plotting it versus depth of the pool or width of the pool. Here they're showing you the different temperatures, right, along the different scan paths. And in the end, we're able to produce these remarkable graphs. Like, this is what we've been missing. This is a high fidelity prediction, right, of what the high fidelity scans might have been using low fidelity data as an input. We're actually seeing now the depth and the width as a function of the sort of whole scan pattern predicted over this entire thing. So what were some of the takeaways? Like, clearly, they noticed that it's not enough to do modeling on a single scan pattern. They know that because they looked at the melt pool, geometry in the center of the scan pattern. They looked at it on the edge of the pattern, and they're not the same thing. So it's important to be able to model the entire pattern. They also noted that this approach, where they take in low fidelity conduction model data and predict the high fidelity model, actually works. They're able with this surrogate model to do reasonably accurate predictions of the high fidelity data. And finally, they point out that this is probably something that can be extended to other approaches where you're worried about industrially relevant scan patterns. So I hope you'll check it out and learn more in the latest issue of IMMI.